All right, so let's start this problem off just how we start every physics problem off, by drawing a picture. I got my wall here. Over here I got my water. There it is, coming out of a hose. They tell us that the initial speed of the water before it smacks into the wall, that is 42 meters per second. And they give us something else. They give us the rate of the water coming out of the hose. And they tell us that that's 50 kilograms per second. So not really sure what this is, but the units at least are those of mass over time. So we'll keep that in mind, see if it comes in useful. They also tell us that we'll assume that the horizontal momentum, the final horizontal momentum of the water after it hits the wall, is 0. So apparently we're only carrying what's going on horizontally like this. And they say, all right, if you assume that, tell me what the force on the wall is. That's the goal here. So what do we have? We know stuff about momentum. We want something about force. We have sort of speed information here, and we've got mass and time sort of mushed together here. So all of those together say probably this is an impulse problem, plus the fact that's the chapter we're in. So impulse, which is J, that's the change in momentum. So the final momentum minus the initial momentum, hey, that's good. There's the final momentum. But impulse is also equal to the average force multiplied by the time, however long it takes to apply this average force to get the momentum to change from whatever it was at the beginning to whatever it is at the end. So force, that's the thing we're interested in. We know some stuff about a momentum. So let's start with this. But there's a problem. This force is going to be the force on the water because we know stuff about the momentum of the water, and we want the force on the wall. But fortunately, the force on the wall is going to be negative the force on the water because it's the water pushing on the wall and the wall pushing on the water. This is true by Newton's third law. Okay, so if we can figure out the force on the water, we'll just do a negative sign. That'll give us the force on the wall. That's the thing we want. So we got to figure out the force on the water. So let's take this definition and that definition of momentum and set them equal to each other because they're both momentum. So the average force multiplied by the time is the final momentum minus the initial momentum of the water. The final momentum, that's equal to 0. So let's go ahead and just write that in. It cancels out, it's 0. So we want the average force. It's going to be the negative of the initial momentum over time. And the initial momentum, we plug in what momentum is. Momentum is mass times the velocity. So mass times the initial velocity, which is still a vector, of course, all divided by time. And so we got the initial velocity here. That's the velocity of the water before it hits the wall. All right, so I guess it's a vector. We gotta decide which way we want to be positive. Let's say going towards the wall is positive. So we can plug in for VI. VI is 42 meters per second in the positive direction, but we need mass and time. We need mass over time, which look, we got it. All right, so we just need to change how we're thinking about this. Don't think of mass and time as separate. Think of it as mass over time times the initial velocity, and we got it all set. This guy, mass over time, is 50 kilograms per second. This guy is positive 42 meters per second. We can go ahead and plug those in. So the average force, this is on the water, just to remind ourselves what we're solving for here, is negative the mass over the time, 50 kilograms per second, times the initial speed in its direction to make it velocity. So it is headed off in what we've called the positive direction. So it's positive 42 meters per second. And 50 by 42 that is 2100. Negative, and that's a positive, but we're multiplying, so pi doesn't matter. So this guy is negative, meaning that it's pointing that way in the negative direction. And the units, they're kilograms, meters over seconds, and over seconds. So kilograms times meters over seconds and seconds again, that's over seconds squared. But kilograms times meters over seconds squared, that's newtons. That's good, because it's force we're looking for. All right, so this is the force on the water, but we're looking for the force on the wall. But because of Newton's third law, the force on the wall is negative the force on the water. So we just take this guy, same magnitude, opposite direction, change that sign. So the force on the wall is going to be the negative of this, or 2,100 newtons. And that's our answer. So how you do these kinds of problems, start with this equation, look at how momentum's changing. That's going to be equal to the force times the time. Do some algebra, be a little bit clever here. They didn't give us the mass or the time, but they did give us the mass over the time. So we can just plug those guys in at once and solve. And then use Newton's third law to say, oh yeah, if we know how much the wall's pushing on the water, we know how much the water's pushing on the wall. Same magnitude, just in the opposite direction. And there you go.